If I flip a coin 10 times, I might get 7 heads. If I flip it 10,000 times, I'll get almost exactly half of those flips as heads. So why does that happen? Why does randomness become predictable the more random events that you do? In this video, I'm going to address some of the misconceptions we have with the law of large numbers. Let's start with intuition. If a coin is fair, we expect half of the time to get heads and half of the time to get tails. This is true for all random events if there are only 2 outcomes. So a lot of people assume that even in a small number of flips of a coin, it should be close to a 50-50 split. But if you've ever actually flipped a coin, let's say 10 times, you'll know that that's just not true. You might get 8 times heads, and other times you might only get 1 time heads. So the intuition is that randomness should balance out quickly, but here's the reality. Randomness does not balance out quickly. In fact, balancing out actually takes a very large number of events or number of tries. In a small sample, randomness looks messy, it looks uneven, and sometimes very surprising. For example, you could flip a coin 5 times and all of them could be heads. Now the chance of that happening would be 0.5 or a half to the power of 5. So a half times a half 5 times. But as the number of trials increases, something powerful starts to happen. The results begin to settle down. They stabilise around what we call the true average. Let's make this concrete with a good example. Imagine I flip a fair coin, so equal chance of heads and tails. After I flip the coin 10 times, I might get 7 out of those 10 as heads. That's a 70% success rate for heads, which is quite far away from the 50% that was our expected value. Let's now consider after 100 flips. I might get, say, 54 heads. That's fairly close to 50%, but it's still not quite there. There's still that 4% difference. However, after, say, 10,000 flips of a coin, I might get 5,012 heads. That's 50.12%, which is extremely close to that 50%. But in comparison, in case 1, we were only 2 coin flips away from actual 50%. In case 2, we were 4 coin flips away from 50%, but it was still a closer probability. In case 3, we were 12 coin flips out away from the actual 50%. But given the number of events, we were much closer to that 50%. So as we can see, the more times we repeat a random experiment, the closer the average result gets to the true expected value. And that's exactly what the law of large numbers says. As the number of trials increases, the average of the results gets closer and closer to the expected value. Or a more simplified version of that, more data doesn't remove the randomness, it reveals the truth underneath it. So why do people get this wrong? Well, there's a few reasons for this. Small samples feel meaningful. If you get heads 4 times in a row, it feels like something unusual has happened because we're expecting it not to actually happen. We're expecting 1 time heads, the next time tails. However, the other reason is we expect the balance too early. We expect randomness to correct itself immediately But randomness doesn't work like that. It doesn't fix short-term imbalance. It only settles in the long run. So let's look at a few examples where this might actually influence or have an impact on your life. Say you complete a test, an exam. If you do just one test, your score might be unusually high or unusually low. But if you did 50 tests, your average score would give a much more reliable picture of your ability. In sports, a player might have an amazing first 5 games, but over the course of a full season, their performance settles to their true level. Or in a survey. This is why surveys need large sample sizes. If you only ask 5 people, the result is very unreliable. It is heavily reliant on those 5 people being a good enough spread across the whole population. If, however, you ask 5,000 people, the average becomes much more accurate. So, the law of large numbers doesn't say that randomness disappears. It says that the patterns emerge from randomness, but only when you have enough data. So, next time you see a small set of data, a few test results, a short winning streak, or even a tiny survey, ask yourself this question: is this just random noise, or is there enough data here to reveal the actual truth? And if you found this interesting, check out this other video where I explain why averages can be misleading. I'll see you there.